Okay, so this video has to do with the next section of your outline called Entropy and Free Energy. So I'm going to quickly go over this because you can read on your own most of this, but just quickly, the enthalpy has to do with an exothermic reaction generally being favored. So that's why we had most of our delta H's as negative. Because remember, an exothermic is a negative delta H. Entropy, however, has to do with the disorder or the dispersal of matter and energy in a system. So, chaos. And we talked about the fact that, in your room or at your house, it's a lot easier to just throw something in the floor than it is to put it back where it belongs. So disorder takes less energy than order. So that is why it's a favored state. So that is a positive delta S. Entropy is delta S. So a positive delta S is favored. Negative delta H, positive delta S. Moving on down, we're not really talking about thermodynamics, does not take into account the rates. We're not talking about rate of reaction. So reviewing the laws of thermodynamics. We've already talked about the first and second law, but there should also be a zeroth law. So basically they came up with the first, second, and third laws, and then they're like, we should have gone back and we should have said this also. So they added it kind of in as an unofficial law called the zeroth law, which simply says, okay, well, if you have a substance A and it is in equilibrium with substance B, and substance B is in equilibrium with substance C, then substance A and C are in equilibrium. All right? So if A and B are equal, B and C are equal in a reaction, then A and C is also in equilibrium. So very simple, straightforward thing. First law of thermodynamics, we've talked about energy can never be created or destroyed, so this is conservation of energy. Second law of thermodynamics, the universe is constantly increasing the dispersal or disorder, so it's always going towards chaos. Third law of thermodynamics is that the entropy of a perfect crystal at 0 Kelvin is 0. So only a perfect crystal would be 0. So delta S is very rarely 0 because there are very, very few perfect crystals. There are always little problems with any crystal. So pretty much you're going to assume that for a delta, you're going to have a number for delta S. It is not going to be 0. All right, entropy. Well, we've already talked about that. It is, it looks at the number of arrangements that are possible to a system. It is very closely related to probability. So it's very closely related to probability. In kind of lay terms, nature spontaneously proceeds toward the states that have the highest possibilities of existing. What this, even in more simple terms, means is that things always go from areas of high concentration to areas of low concentration. So if you have a gas that is all packed together on one side, you open the valve between this side that is packed with gas and this side that has no gas. This is eventually and very quickly going to move over to where you have the same number of molecules of gas on each side. So it's going to go to equilibrium. And that has to just do with, that is easier. That is more disorder, and it is easier for the system to maintain than to try to keep a high concentration over here. So some very simple, kind of wrap it up on entropy, is that the greater the disorder in a system, the larger the entropy. So the bigger the delta S. The greater the entropy of a substance always increases as you go from a solid to a liquid to a gas. So solid has the lowest energy, or lowest delta S. Liquid has the next. Gas has the highest delta S. If you dissolve a solid or a liquid, it is going to increase the entropy. So if you go from a solid to a liquid, you increase the entropy. If you go from a liquid to a gas, you increase the entropy. The only thing that is an exception to that are carbonates. Carbonates actually bring more order to the system. Entropy generally increases with molecular complexity. So if you look at these two crystal structures, you've got KCl, which is just 2 atoms, versus CaCl2, which has 3. If you have more atoms, you have more electrons, which means more disorder. So that is more delta S. And increasing the number of moles of particles also increases entropy. All right, so here's some examples. All right, we take sugar and we add it to water to form a solution. So we are going from a solid to a liquid, and that increases your delta S. So that would be a positive delta S. Here we go from iodine vapor, which is a gas. It condenses on a cold surface to form crystals, which would be a solid. So we're going from a gas to a solid. Remember we talked about this. You go from a solid to a liquid to a gas. You increase in entropy the whole way. So if we're going back this way, we're going back towards order. So this is going to be a negative delta S. All right. The Hess's law equation also applies to delta S. So this is the same thing we did with the delta H's. So you say delta S of the reaction equals the sum of delta S of the products minus the sum of delta S of the reactants. The only thing that has changed is the unit. This is joules per mole times K. So let's look at this equation. Okay. We're going to use our delta S equals our sum of the products. I should say the delta S of the products minus the sum of the delta S of the reactants. So, same thing we did yesterday or Friday in class is 2 times SO3, because that's our product here, minus the sum of the reactants. 2 times SO2 plus O2. All right. Now, then all we do is we look here. We're given the data of our delta S's. So we have 2 times SO3. SO3 is here. It has a delta S of 256.6 minus 2 times SO2, and its delta S is 248.1, plus oxygen's delta S, which is a 205 0.3. When you put this into your calculator, 2 times 256.6 minus 2 times 248.1 plus 205.3, we get negative 188.3, and this is joules per mole times K. All right. So that is just your simple delta S. Well, you can also deal with delta S of the whole kind of universe of your reaction. Well, you can deal with delta S also in terms of whether it is the system delta S, so delta S of the system, which is the heat transferred over the temperature, which equals Q over T. You can also say, because Q is also equal to delta H, that is delta H over T. So that's your delta S of the system. Or you can also do delta S of the surroundings. So the system is, this is your beaker or whatever that your reaction is occurring in. The surroundings would be everything around it. And this is going to be negative delta H over T. All right, so if we look at the formula, or the exercise 3 rather, you're looking at two different reactions. We have reaction 1, reaction 2. And they want you to find delta S for each of these. At 25 degrees Celsius, which is 298 Kelvin, and 1 atmosphere. So we kind of ignore the atmosphere pressure. So for number 1, our delta S of the surroundings is equal to negative delta H over T. Well, they gave us our delta H. So it is negative delta H, which is a negative 125. And that is kilojoules per mole. Over T, which is 298 Kelvin. When you put that into the calculator, you're going to get 0.419 kilojoules per mole times K. Well, delta S is always in joules. So we need to change this to joules. So you either multiply by 1,000 or move your decimal point 3 places. So this is equal to 419 joules per mole times K. Well, number 2, our delta S of our surroundings, again, equals negative delta H over T, which equals negative, and our delta H this time is a positive 778 over T. The T is the same at 298. When you put this in, you get a negative 2.61 kilojoules per mole times K. Same thing, convert that to joules, and you should get 2,610 joules per mole times K. And that's if it asks you for the delta S of the surroundings. All right, so again, just in summary, a positive delta S means that there's more disorder. A negative delta S means that there's less disorder. More disorder means that you have more moles of gas. You have more electrons. You are going from a solid to a liquid or to a gas. Any of those situations is going to give you a more positive delta S. A negative delta S, you're going to the opposite direction. You're getting more ordered. You have fewer moles, that type of thing. Whether a reaction is going to occur spontaneous or be favored is looking at the delta S of the universe. If the delta S of the universe is positive, then the reaction is thermodynamically favorable. If it is negative, it's not thermodynamically favorable. And you get the delta S of the universe by taking your delta S of the system plus your delta S of your surroundings. You add those together, and that gives you your delta S of your universe. All right, so they give you this example looking at hydrogen and oxygen and producing water. If you ignite the hydrogen and oxygen, the reaction is extremely fast. It produces a delta S with a negative 88.9, though. And that is because you're going from 3 moles of gas to, that should actually be 1 mole of gas, because you've got 2 plus 1, that's 3, going to 1 mole. So that is becoming more ordered. So that means that it is a negative delta S. However, it says that the reaction proceeds very quickly, which would seem to say that this is a spontaneous reaction once you get it going. And it actually is. So you have to actually look at the entropy of the surroundings to find out what is going on. All right? And we want to eventually get to your delta S of the whole universe, the whole area around it. So what we do, your delta S of surroundings equals Q over T, which of course, remember, is delta H over T. So they gave us, if you work it out and you look at it, if we want to find the delta S of the surroundings, delta H surroundings over T equals your negative delta H of your system over T. Okay? Because your surroundings and your system have to be equal. So the delta S of your surroundings is going to be of delta H of your surroundings is a plus for 83.6. And if you calculate delta S surroundings from that, you take your delta H over T, and you get 1,620 joules. So that's a positive delta S. If we find the delta S of the universe, though, that is the system plus the surroundings equals our universe. So negative 88.9 plus the 1,620, that gives us 1,530 joules per mole reaction times K. So even though the entropy of the system declines, the entropy change for the surroundings is so very large that the overall change for the universe is positive. So a process that's thermodynamically favorable in spite of a negative entropy change, as long as it is extremely exothermic. So sufficient exothermicity offsets system ordering. So even though this first appears like it is becoming more ordered, actually it is increasing disorder for the whole universe because of the fact that the surroundings, the delta S for the surroundings is so large. All right, free energy. Looking at delta G. We have dealt with delta G with the electrochemical equations. And remember, a negative delta G means that it's thermodynamically favored. That is a spontaneous reaction. So if you have, again, a negative delta G, it means it's spontaneous. So we use the same equation again, that delta G of the reaction is equal to the sum of delta G products minus the sum of delta G reactants. So if it asks for the delta G naught of the reaction, or the delta G of formation, then you can use that sum equation. Also, another delta G equation is delta G equals delta H minus T delta S. So you've got H, of course, is your delta H from the table, minus T for temperature, and your delta S for your entropy. You will also use the delta G equals negative rat link, which we used in electrochemistry as well. If you need to solve for K, that would be how you would solve for K. You might also use the delta G equals negative NFE naught. If you needed to solve for N or F or E naught. So exercise 4. Calculate the free energy of formation for the oxidation of water to produce hydrogen peroxide given the following information for delta G values. All right, so we are going to use delta G naught F. So the delta G naught F, that means that we're going to use the sum reaction. The sum of delta G naught products minus the sum of delta G naught reactants. And I just work it out. So there's my product, 2 times H2O2 minus the sum of my reactants, 2 times H2O plus O2. All right, and also the same with delta H. If you have an element by itself, for delta G, it is a 0. And you know that by just looking here, that O2 is equal to 0. So now we just substitute in our numbers, 2 times H2O2, that's negative 27.2, minus 2 times our H2O, which is negative 56.7. And if you work that out, you should get 59. And this is kilocalories per mole reaction.